The success of machine learning models heavily depends on the quality of the features used to train them. Feature engineering is the process of transforming raw data into features that are suitable for machine learning models. It is the process of selecting, extracting, and transforming the most relevant features from the available data to build more accurate and efficient machine learning models. These techniques help to highlight the most important patterns and relationships in the data, which in turn helps the machine learning model to learn from the data more effectively. A feature or variable is an individual measurable property or characteristic of a data point that is used as input for a machine learning algorithm. Features can be numerical, categorical, or text-based, and they represent different aspects of the data that are relevant to the problem at hand. We engineer features for various reasons, and some of the main reasons include: improve user experience. The primary reason we engineer features is to enhance the user experience of a product or service. By adding new features, we can make the product more intuitive, efficient, and user-friendly, which can increase user satisfaction and engagement. Competitive advantage. Another reason we engineer features is to gain a competitive advantage in the marketplace. By offering unique and innovative features, we can differentiate our product from competitors and attract more customers. Meet customer needs. We engineer features to meet the evolving needs of customers. By analyzing user feedback, market trends, and customer behavior, we can identify areas where new features could enhance the product's value and meet customer needs. Increase revenue. Features can also be engineered to generate more revenue. For example, a new feature that streamlines the checkout process can increase sales, or a feature that provides additional functionality could lead to more upsells or cross-sells. Future-proofing. Engineering features can also be done to future-proof a product or service. By anticipating future trends and potential customer needs, we can develop features that ensure the product remains relevant and useful in the long term. Processes involved in feature engineering. Feature engineering in machine learning consists of mainly 5 processes: feature creation, feature transformation, feature extraction, feature selection, and feature scaling. It is an iterative process that requires experimentation and testing to find the best combination of features for a given problem. 1. Feature creation. Feature creation is the process of generating new features based on domain knowledge or by observing patterns in the data. It is a form of feature engineering that can significantly improve the performance of a machine learning model. Types of feature creation. 1. Domain-specific. Creating new features based on domain knowledge, such as creating features based on business rules or industry standards. 2. Data-driven. Creating new features by observing patterns in the data, such as calculating aggregations or creating interaction features. 3. Synthetic. Generating new features by combining existing features or synthesizing new data points. 2. Feature transformation. Feature transformation is the process of transforming the features into a more suitable representation for the machine learning model. This is done to ensure that the model can effectively learn from the data. Types of feature transformation. 1. Normalization. Rescaling the features to have a similar range, such as between 0 and 1, to prevent some features from dominating others. 2. Scaling. Scaling is a technique used to transform numerical variables to have a similar scale so that they can be compared more easily. Rescaling the features to have a similar scale, such as having a standard deviation of 1, to make sure the model considers all features equally. 3. Encoding. Transforming categorical features into a numerical representation. Examples are one-hot encoding and label encoding. 4. Transformation. Transforming the features using mathematical operations to change the distribution or scale of the features. Examples are logarithmic, square root, and reciprocal transformations. 3. Feature extraction. Feature extraction is the process of creating new features from existing ones to provide more relevant information to the machine learning model. This is done by transforming, combining, or aggregating existing features. Types of feature extraction. 1. Dimensionality reduction, reducing the number of features by transforming the data into a lower dimensional space while retaining important information. Examples are PCA and TSNE. 2. Feature combination. combining two or more existing features to create a new one. For example, the interaction between two features. 3. Feature aggregation, aggregating features to create a new one. For example, calculating the mean, sum, or count of a set of features. 4. Feature transformation, transforming existing features into a new representation. For example, log transformation of a feature with a skewed distribution. 4. Feature selection. Feature selection is the process of selecting a subset of relevant features from the dataset to be used in a machine learning model. It is an important step in the feature engineering process as it can have a significant impact on the model's performance. Types of feature selection. 1. Filter method. Based on the statistical measure of the relationship between the feature and the target variable. Features with a high correlation are selected. 2. Wrapper method. Based on the evaluation of the feature subset using a specific machine learning algorithm. The feature subset that results in the best performance is selected. 3. Embedded method. Based on the feature selection as part of the training process of the machine learning algorithm. 5. Feature scaling. Feature scaling is the process of transforming the features so that they have a similar scale. This is important in machine learning because the scale of the features can affect the performance of the model. Types of feature scaling. 1. Min-max scaling. Rescaling the features to a specific range, such as between 0 and 1, by subtracting the minimum value and dividing by the range. 2. Standard scaling. Rescaling the features to have a mean of 0 and a standard deviation of 1 by subtracting the mean and dividing by the standard deviation. 3. Robust scaling. Rescaling the features to be robust to outliers by dividing them by the interquartile range. Here, we are seeing a real-life example, where we transformed or feature engineered the original dataset into model train-ready dataset. Techniques used in feature engineering. 1. Handling missing values. Missing values are data points that are absent for a specific variable in a dataset. They can be represented in various ways, such as blank cells, null values, or special symbols like NA or unknown. These missing data points pose a significant challenge in data analysis and can lead to inaccurate or biased results. Data can be missing for many reasons like technical issues, human errors, privacy concerns, data processing issues, or the nature of the variable. Types of missing values. 1. Missing completely at random. MCAR is a specific type where whether a value is missing or not has nothing to do with the values of other variables or the characteristics of the data point itself. 2. Missing at random. MAR is a type of missing data where missing mechanism is not entirely random, but it can be predicted based on the available information. 3. Missing not at random. MNAR is the most challenging type of missing data to deal with. The reason for the missing data is informative and directly associated with the variable that is missing. Methods for identifying missing data. Is null, identifies missing values in a series or data frame. Not null, check for missing values in a pandas series or data frame. Where true indicates non-missing values and false indicates missing values. Info displays information about the data frame, including data types, memory usage, and presence of missing values. Is NA. It returns true for missing values and false for non-missing values. Drop NA. Drops rows or columns containing missing values based on custom criteria. Fill NA. Fills missing values with specific values, means, medians, or other calculated values. Replace. Replaces specific values with other values, facilitating data correction and standardization. Drop duplicates. Removes duplicate rows based on specified columns. Unique. Finds unique values in a series or data frame. Missing values can be represented by blank cells, specific values like NA or codes. There are several strategies for handling them. Here's an overview of some common approaches like imputation methods, flag variables, drop records. First, we will see imputation methods. These are to replace missing values with estimated values. Replacing missing values with estimated values, it preserves sample size, doesn't reduce data points. but it can introduce bias. Estimated values might not be accurate. Mean, median, and mode imputation. It replaces missing values with the mean, median, or mode of the relevant variable. It is easy to implement. It doesn't consider the relationships between variables. Forward and backward fill. It replaces missing values with the previous or next non-missing value in the same variable. It preserves temporal order. It can be inaccurate. It assumes missing values are close to observed values. Interpolation techniques. It estimates missing values based on surrounding data points using techniques like linear interpolation or spline interpolation. Linear interpolation method performs linear interpolation on the desired column of the data frame. Linear interpolation estimates missing values by considering a straight line between two adjacent non-missing values. Quadratic interpolation method performs quadratic interpolation on the desired column. Quadratic interpolation estimates missing values by considering a quadratic curve that passes through three adjacent non-missing values. These techniques are more sophisticated than mean-median imputation. It captures relationships between variables. It requires additional libraries and computational resources. Now, let's see binary flag for missing values. It is possible that knowledge of whether a row contains a missing value or not will be useful to the model when making a prediction. One approach to exposing the model to this knowledge is by providing an additional column that is a binary flag indicating whether the row had a missing value or not. 0. Row does not contain a missing value. 1. Row contains a missing value, which will be imputed. This can be achieved directly on the loaded dataset. First, we can sum the values for each row to create a new column where if the row contains at least one nan, then the sum will be a nan. We can then mark all values in the new column as 1 if they contain a nan, or 0 otherwise. Finally, we can add this column to the loaded dataset. Third is drop records method for missing values. The simplest and easiest approach to handle missing values is to remove the rows or columns containing missing values in the dataset. Removing too many observations can reduce the statistical power of the analysis and lead to biased results. When we use this technique, if a particular column is missing many values, you have a huge dataset. Then, removing 2 to 3% rows, columns won't make much difference if output results do not depend on deleted data. If datasets have highly skewed distributions, removing rows with missing values will be the best choice compared to imputation. This approach should be used in the above scenarios only and is not recommended much. First, let's understand why encoding is necessary. Machine learning algorithms. Most machine learning algorithms, such as linear regression, support vector machines, and neural networks, require numerical input. Categorical data needs to be converted into a numerical format to be used effectively. Model performance. Proper encoding can significantly impact the performance of a machine learning model. Incorrect or suboptimal encoding can lead to poor model performance and inaccurate predictions. Data preprocessing. Encoding is a crucial step in the data preprocessing pipeline, ensuring that the data is in a suitable format for training and evaluation. Encoding techniques in Sklearn-Libel encoding, a simple and straightforward method that assigns a unique integer to each category. This method is suitable for ordinal data where the order of categories is meaningful. Use case. Applicable for cases in which the ordering of categories has analytical relevance. One hot encoding. This converts categorical data into a binary matrix where each category is represented by a binary vector. This method is suitable for nominal data. Use case. Most appropriate for those situations where the categories do not have an inherent order or there is a clear distinction between them. Ordinal encoding assigns a unique integer to each category, similar to label encoding, but it is specifically designed for ordinal data. It ensures that the order of categories is preserved. Use case. Used where categories are almost in order, meaning that if there is an order then it has to follow a certain order that is recognized. Binary encoding. In the context of categorical feature encoding involves converting each category into a binary code and representing it as a sequence of binary digits 0 and 1. It assigns a unique integer to each category. Converts the integer to binary code. creates a set of binary columns to represent the binary code. Frequency encoding replaces each category with its frequency in the dataset. This method is useful for high cardinality categorical features. Use case may be useful in recording the extent to which a particular category was a concern in the statements made by the research participants. Choosing the right encoding method depends on the nature of the categorical data and the specific requirements of the machine learning model. Here are some guidelines to help you choose the appropriate method. Nominal data. Use one-hot encoding or frequency encoding. Ordinal data. Use label encoding or ordinal encoding. High cardinality features. Use target encoding or frequency encoding. Avoiding overfitting. Be cautious with target encoding and consider using cross-validation techniques to prevent data leakage. Congratulations! You are now the expert on what is feature engineering, how to handle missing values in A data, how imputation method works in feature engineering.